Welcome, everybody. Today, we are going to be talking about the basics of gamma cameras, basic gamma camera operation, some concepts of corrections, and how does a camera function. So, the purpose of nuclear medicine, to start at the real basics, the purpose of nuclear medicine is to be able to look at specific functions or organs in a patient and use gamma rays to determine that. The detection of these emissions is what we're going to use to determine if the process is working properly, if the process is not functioning properly, and basically look at the functions. To detect these emissions, we're going to need a specialized piece of equipment. We need to be able to look at where the events originated from. We need to be accurately able to count them. We also want to make sure we eliminate or reject anything that is undesired, any undesired emissions. Some of the pictures down here on the bottom are of exams or scans that would be somewhat common. Left-hand picture down at the bottom is of a total body scan. The middle one is a renal flow, and the right set is lung scans. So these are kind of the images and the quality of the images that you can expect out of a gamma camera. So when we talk about a gamma camera, we kind of have some criteria that we want to be sure to accomplish. We want to make sure that our radiation exposure for the technologist and for the patient is as minimal as we can get. We obviously don't want to expose a patient to more radiation than is necessary. We want to make sure that this camera or our detection device is able to provide a uniform display for a uniform input. We want input to equal output. Without that, we can't trust what we're seeing. We also want to be able to identify the ISO peak or the energy of the isotope that is being utilized. That is crucial because without that ability, we can't distinguish between good events or actual events and garbage events. We want the geometry of the images to be accurate. If I have a circular object, I want it to be circular. I don't want it to be oblong. So we want that geometry to be good. We want to be able to distinguish between the good and the real events from the bad events, and that relates back to item number 3, the ISO peak. If we're able to identify that ISO peak, we can eliminate scatter radiation, background radiation, other sources. We also want to be able to identify the exact origin of a gamma ray. And we need that in space. We need to be able to determine that in a 3-dimensional space. The reason that is because we have certain processes or certain exams that reproduce a 3-dimensional response or 3-dimensional image of an object, let's say the heart. We want that 3-dimensional object or heart to be true. So we need to be able to accurately determine that. And lastly, we obviously want to be able to determine size. If I am looking at a defect, we want to be able to identify that defect as a specific size. That will help the radiologists, the doctors, to understand what they're looking for or what they need to do. Before there was what we'll call a modern gamma camera, there was a gamma camera or a detection device called a rectal linear scanner. That was developed around 1950. It has issues. It's a very simplistic device. If you look at the picture down at the bottom, we have a detecting element that is directly coupled mechanically to a display generating device. Now, the display generating device could be a lamp exposing film. It could be an electrode arcing through a temperature sensitive paper, something like that. The way it operates is it literally scans left, moves up a little bit, right, moves up a little bit, left, moves up a little bit, right. It's literally scanning almost like an Etch-a-Sketch across the patient. It has some inherent defects or some problems with it. One of them is that we have a device that has limited time over any particular area. And that limited time is going to mean that I probably am going to be increasing my dosage to the patient, which was kind of one of the criteria we didn't want. We want to keep our dose low. So how fast I scan over a patient is going to directly be affected by the dose that I give the patient. If I scan really slow, obviously the patient has to be extremely still. We all know patients don't want to be still. Another reason that these aren't real good is they have pretty poor resolution. That is a problem with the mechanical aspect to it, and also the size of the detecting element. And it's going to introduce or impart artifacts into the images. They are going to be mechanical artifacts in the images. So we have a couple scans here of a rectal linear scan. The left one is a lung scan, the right one's a thyroid scan. That left one, if you look at it, you can see, well, actually in both images, we can see horizontal lines in it. That is due to that scanning nature, where it made a sweep across, moved, made another sweep across, moved up, made another sweep across. One of the problems that's inherent in these type of images is that whatever is produced onto this image or onto the display device, our film or a paper, that's all you get. It's going to be what you get. So if you look at their lung scan, there's not real good definition in there. I can see the outside shape of it, but the central portions of it are pretty poor. There's not a lot of contrastability, and I cannot adjust it. It's fixed onto paper. So your setup, as well as your dosage, is crucial to produce a good quality image in these things, or as good a quality as it can. Well, in about 1957, a guy by the name of Dr. Hal Anger developed what we consider the principles of the modern gamma camera. And what we're going to do, or what Dr. Anger come up with, is we're going to use PMT signals, photomultiplier signals, from an array of photomultipliers, which are positioned on a large sodium iodide crystal. The purpose of that is to create one large detecting element instead of a bunch of small detecting elements. Since we're using individual tubes, we actually be using a weighted averaging of the outputs of the photomultiplier array to help us determine the scintillation location, and we'll be using the summation of all of the photomultiplier outputs to determine gamma energy. A lot of times you'll hear the term Anger theory or Anger technology. That is referring to this concept that we're dealing with. So we have a kind of a 10,000 foot view of a camera, how it images. First of all, it starts out with, we're going to inject isotope into a patient. That isotope in the patient is going to localize into an area. Hopefully that localization of the area is, I'm sorry, I got distracted here. We have isolation of or localization of the isotope into an area. That localization, that uptake is going to then emit gamma rays. The gamma rays are going to go everywhere. We know radiation goes in every direction. And since it goes in every direction, there's inherent problems in that. We also are going to have issues with background radiation, background scatter, etc. And so we need a way of isolating these desired gamma events. Well, we introduce a device called a collimator. What this does is it forces all of the gamma rays to be perpendicular to each other, or parallel to each other, and perpendicular to the crystal in order to be able to pass through the collimator and interact with the crystal. Once it hits the crystal, the photomultiplier tube will detect it. We'll use weighted averaging to generate a position. That generates an image for us. So now the left-hand part of the heart's emissions obviously impact further left on the detector, and the right-hand part of the heart's emissions emit or are detected by a different portion of the crystal. This is critical in determining or creating an accurate image. So from there, we also want the ISO energy. We're going to take the summation of all of the gamma events. Every gamma event that makes it through the collimator to the crystal, we're going to take those events and we're going to create, or we're going to identify the photo peaks of them. So I have a little spreadsheet type thing over on the right-hand side. That spreadsheet is saying that it's frequency of the impact, how often, and the energy of the impact. So if I have one gamma energy that struck at 134 keV, I have one gamma energy that struck at 142 keV. Those KeVs and everything in between, by plotting how many of a particular energy struck and isolating to that specific keV, if I plot that, I will get the graph down below, our photo peak. That photo peak is telling me where the primary energy of the emissions from that HART are. Again, that is important in identifying or discriminating from other energy isotopes. We don't want, obviously, energy isotopes to be coming from a poor absorption, which would be considered scatter. That would be the lower type bump. We don't want it to be from reflections. We don't want it to be from other sources, cosmic radiation or whatever. That lower peak that you'll notice, that is going to be something that is inherent. You're going to see that in peaks, and it is called Compton or scattering peak. It is something that we don't want to be imaging. So our first detection device, the first thing to interact with the gamma ray is going to be our collimator. A couple of pictures of different collimators. And we said that gamma rays are emitted from a source in all directions. And so therefore, by definition, they diverge, they go in all directions. The top of the bottom picture there, or the top picture, I have two blobs of radiation and they're emitting gamma rays. Those gamma rays are going everywhere. So the resulting detection surface just sees a mass of detections. It is not really identifying or defining the source location. By placing a collimator in the way, only the rays that are perpendicular to the detection surface are allowed to pass through. Obviously, this cuts down on a lot of counts, but only the rays that are perpendicular pass through. So my blobs on the right then become identifiable shapes on the left after they pass through the collimator. A collimator, as I said, can be thought of as a discriminator, and your gamma rays must be perpendicular to the collimator in order to pass through. There are two main technologies used in collimator construction. There's a corrugated foil type construction, or septa, and there's a cast type construction, or septa. The cast type construction is, if you think of a plate or a flat surface, a perfectly flat surface with tens of thousands of little pins or protrusions sticking up, and then if I was to pour lead over top of that, when the lead cools, if I extract those pins from that cooled lead, it will leave individual tiny holes. Tops and bottoms are machined, and I will get a cast septa. Very expensive to make, but very high quality. Foil septa, on the other hand, you can think of it as like a corrugated roof type surface that are offset from side to side. And by placing those offsets in the proper position, what you will get is the effective purpose or the effective function of the same thing as a corrugated, or the collimator, the cast septa. The problem is that these corrugations have to be glued together, and so there is a very slight penetration ability for a gamma ray to sneak in between those corrugations, and so you can see some slight streaking in the images. They are much cheaper to make, much more readily available, but they're not quite as high quality. They're actually more prevalent though, because the degradation in image quality is not that bad. So collimators also come in septal thicknesses or septal lengths. The septal thickness, in the picture in the top right, I have a collimator that would be a high energy collimator, probably medium to high resolution. And you'll notice the septal walls are quite thick. I have a lead pencil laying down there as a reference. The septal walls are quite thick on that. The reason is that septa is generated or was created for a high energy or a medium energy isotope. Because the isotope has more penetrating power, I need those thicker walls to block it. The top little blocks on there are actually lower energy general purpose collimator septa. You'll notice that the tiny holes, the holes are much tinier, and you notice that it's much shorter. Again, there is a ratio between hole size and length on both of those, but the high energy or the medium energy collimator is not, I'm getting distracted. The medium energy collimator has septal walls that are much thicker. They are chosen to cause or to allow for minimal penetration of the gamma rays based upon the isotope we want to use, and the septal or isotope or the septal hole thickness or diameter is chosen for efficiency. The diameter and the wall thickness have to be a given ratio. I don't want to block or obstruct too many gamma rays. And then the septal length is going to affect my resolution. Collimators are made out of lead, and collimators can be damaged easily. They're very fragile by nature. They're susceptible to careless handling, accidental impacts. On the picture that you see there, we have a dime resting on a low energy collimator. You notice the defect or the divot into it, and you can see the obvious result of the septal walls or the top of the septa is being smashed or smushed. That's flattening them out. It's blocking more radiation than it should. So the result is gamma rays in those areas aren't going to penetrate through. And so I will have a cold area or a cooled area in my image. Obviously undesirable. So care needs to be taken when handling collimators. Some machines have automated exchangers. You want to make sure that no parts, screws, washers, whatever, get impacted into the collimator. Also, you don't want anything to hit it any other way. So the next device is the crystal, the next device that we're going to be dealing with. I've got a couple pictures of crystals here. It is the device that is going to detect the gamma rays. It's going to create the scintillations. So as the gamma rays pass through a collimator, they're going to react with the crystal, and they're going to scintillate. Basically, when they scintillate, they're going to create photons. It's a very light blue hue is what you're going to see. But those gamma rays impacting, creating photons is a proportional thing to the energy of the original gamma ray. So if I have a gamma ray that strikes with a high energy, it's going to create more light. Low energy, less light. The thickness of the crystal, though, has to be considered. When we're dealing with gamma rays, if I have too high of energy, it has more of a probability of penetrating through the crystal without an actual interaction with the crystal. And so that's going to be a bad thing. So for higher energy, if you're doing primarily higher energy studies, you're going to want a thicker crystal. Most studies, or a lot of studies nowadays, are done with technetium. It's a fairly low energy isotope. So 3/8 is a very, very common thickness of crystal to be used, especially in cameras that are cardiac specific. They're going to be probably using 3/8 inch crystals. The crystal is a grown item. Picture on the right is an example of an ingot that has been grown. Think of it as sugar water in a string. You can grow crystals on it. This is not grown that way, but they do grow crystals in a manner that is analogous to that. What we do is we take, and once we have an ingot, or the manufacturer, once they have an ingot, they will slab it, or they'll slice slices of it, kind of like slicing cheese, and those slices will be used. Now this crystal is sodium iodide doped with thallium, and that is pretty much well, that is predominant through the industry until we get to some other forms of imaging, such as solid state detectors, stuff like that. But in normal gamma chemistry, where you're using photomultiplier tubes, we're going to be using sodium iodide doped with thallium. So this construction element, there's some issues that we have to deal with. First of all, the crystal itself, it is very fragile. It's much more fragile than glass. It will crack or break very easily. Secondarily, it's very hygroscopic. It absorbs moisture. It wants moisture. It craves moisture. And so it's got to be protected from that moisture. Third thing is we need to protect it from light. We need to protect it from light because it will oversaturate the crystal and cause the crystals to not function properly. So we need to do that. So we got our slice of crystal there. And what we're going to do is we're going to put an aluminum cover and some flanges on one side of it. So the flanges are off to the left and the right. The aluminum cover is on the bottom of the crystal material itself. The reason we use a very thin layer of aluminum there is we need the gamma rays to be allowed to penetrate while blocking light sources. So we need it to be blocked from light. We need gamma rays to penetrate. And thirdly, we need that there to help block moisture. Now, we'll talk about the moisture again later. And then we have our mounting flanges. So what I've got is the picture in the middle there, identifying, I just took a snapshot of the corner of the crystal. So we have the actual crystal itself, the actual part that is doing the detection. And then you'll see a dark outline. And then you have the flange area. Thirdly, we have the third part, or the third main part of a crystal is the glass window itself. The glass window is what is going to be the surface which the photomultiplier tubes attach or are coupled to. This allows the photons to pass from the crystal as scintillations occur. They'll pass from the crystal to the photomultiplier tubes. It is providing some rigidity. Actually, glass is significantly strong if it's constructed properly. It is helping to block moisture, and it has a seal between the aluminum flange and the glass. There's going to be that silicone seal. Now, as I said, these things are extremely hygroscopic. So the way that they're actually constructed is we will take the crystal and it will be dehydrated. All the moisture will be sucked out of it. Aluminum flange will be placed on it. Glass will be placed on it. It'll be sealed up in a very quick fashion or in a moisture controlled environment so that it is as dry as possible, and that way it'll last as long as possible. When a gamma ray strikes a crystal, it's going to do one of three things. It may pass right through it. It might not interact with the crystal at all. And the result is obviously nothing, no scintillations. The gamma ray might strike the crystal, in which it's going to interact with the atoms in it, and it's going to, and in the case where it strikes crystal and gives off some of the energy, what you're going to get is a partial absorption of the true energy. And so we're not going to get a real output. We're going to get part of that Compton peak that we talked about. The third interaction is we have the gamma ray that strikes a crystal, it interacts with the atoms, and it gives all of the energy of the gamma ray into the crystal. When it does that, it creates a true energy response or a true scintillation, which is going to give us a true photo peak for emissions. The important points to remember about a crystal is they are a hermetically sealed environment. Do nothing to cause a puncture into that environment. You can puncture through the aluminum. That's bad, very bad. You could mess around with that silicone seal, very bad. Don't do it. Also, note that they are very fragile in nature. I said they're much more fragile than glass, and they are. Things as simple as an impact can break them. One thing that also people don't think about always is that temperature change can break them. Most OEMs of crystals will tell you that approximately a 5-degree change per hour can cause a crystal to crack or fracture. Now, I've seen temperature changes faster than that, didn't hurt the crystal, but That's their standard. They're saying do not exceed 5 degrees of temperature change per hour. So that means our environment needs to be kept stable. The crystal is a grown item, and so it is not perfect in response. So I might have one area of the crystal that responds differently from another area of the crystal. And this is going to be important down the line. And that affects not only the X and Y axis, but the thickness aspect of it also. When I have a scintillation or a light burst, it is going to be detected by more than one photomultiplier tube. In fact, in theory, every tube sees every gamma event. Not in reality, but the scintillations will be seen by more than one photomultiplier tube. Lastly, hydration. Again, back to our hermetically sealed item, hydration is an issue. If you have hydration, what it causes is it causes yellowing of the crystal. That yellowing of the crystal is going to decrease the crystal sensitivity and is going to increase nonlinear responses to our gamma events. The light isn't going to be as bright because it has to fight through that yellowing. And so it's going to respond incorrectly. So some parts, or just kind of give you what a crystal looks like on the outside, the aluminum cover, top left picture. It is what the customer will see. That is what the field service engineer will see. It's just a very shiny aluminum surface. Sometimes they put covers, your plastic over them, where you don't see the aluminum, but that is really what's under the plastic. The other side of the crystal, the important side of the crystal to the photomultiplier tubes, is the glass surface, and that is where your PMTs are going to mount. Now, the crystal in the top right does not have hydration. If it did have hydration, what you would see is something down towards the bottom there. The hydration in the left picture is actually growing in or creeping in from the outside edge, basically the surface between the flange area and the actual crystal itself. The flange area would be the bluish part. The crystal itself is the area below, and that is hydration that is creeping in from the outside. So some moisture has gotten in through the seal, or there was a small amount of moisture that was never dried out, but somehow some moisture has gotten in there, and it is starting to yellow the crystal in a linear fashion in towards the center of the crystal. One other aspect that you can see in crystals is very localized hydration. Again, that is from a drying process usually, but that localized hydration will cause artifacts as spots. Instead of being an area, it'll be just a spot that starts and it might grow and grow. A lot of times we'll call those measles, kind of reminiscent of when kids have measles, they get the spots on them. These are spots of yellowing. The left-hand picture is just a spot on a crystal itself. The right-hand portion of that picture is actually looking down through the mu metal shield between tubes on a square tube. And there was 2 hydration spots under one tube. So we've made it through the collimator. We've impacted the crystal. The crystal's causing scintillations. We're going to hit photomultiplier tubes. Photomultiplier tubes come in many shapes and sizes. We got a picture of a circular one. We got a picture of a square one. There's one kind of not really an octagon, not really a whatever, but they're octagon shaped. There's all kinds of shapes and sizes, lengths. Just depends on the manufacturer, depends on many things. So an overall of a photomultiplier tube, what is it doing? Well, what we have is we have a photocathode, goes through a focusing grid. It's going to run through some stages of dinodes, and it's going to go to an anode. That's the basic principle of every photomultiplier tube, that basic principle. Now, again, different shapes, sizes, whatnot, but that's a basic principle of it. So if we're going to take a tube and break it apart, on the left-hand side, I took a Siemens tube, and I broke the glass off it, and I took one of the mounting surfaces off so you could actually see the physical dinodes themselves. So we have our photocathode would be down at the very, very bottom, and then we have the individual stages of dinodes up to the anode. The middle picture is showing us a square photomultiplier tube. I believe that's from a GE. That square photomultiplier tube, I'm indicating the photocathode surface. Now, if I take that photocathode surface and I flip it up on end, what I will see is the right-hand picture. The right-hand picture is showing me the photocathode surface, which is the goldish part. If you look at the goldish part, actually it's a very thin film of material that is basically electrostatically adhered to the surface. If I was to it's a vacuum inside the photomultiplier tube, if I was to let the air into that, that would disperse and it would instantly go from this nice golden color to a silver color. But so in this particular picture, I have a good vacuum in the tube. I still have my photocathode there. It's the entire front glass surface is the photocathode. In the central ring, the central circle area, that is our focusing grid. It's not real evident in here, but there is some little fine mesh wires interacting in between that circle. And then down in the center of the focusing grid is the first stage dynode. That is where the electrons that are going to be emitted from the photomultiplier or from the photocathode are going to interact on that first stage dynode. So if I was to describe this verbally, how a photomultiplier tube functions, basically we got a gamma event, strikes a crystal, it's creating photons. These photons get, when they strike the photocathode, they're going to emit or knock electrons free. Those electrons are going to get sucked towards the first stage dynode. A number of electrons is directly proportional to the amount of light. If I have more light hitting the photocathode, you're going to see more electrons emitted. So I have the photocathode emitting electrons. These electrons, they rush towards the first stage, the first dynode stage, and that's because of a high voltage potential. They're going to strike that dynode. When they strike the dynode, think of it as a truck hitting a brick wall, sprays bricks everywhere. Okay, so they hit that first stage dynode, they're going to eject more electrons. So one electron might eject 10. So it's an amplification factor there. So the first stage dynode, all those electrons are getting ejected. When they get ejected, they see the next highest potential. They see the next dynode, and they're going, gee, let's all go there. So those ejected electrons are drawn to that next stage high voltage. They'll strike that dynode. Again, what happens? We're going to eject more electrons yet. Those ejected electrons are going to be drawn to the next high voltage potential, the next dynode. They will strike that dynode, and et cetera, et cetera. We're going to go on and on until the final output, or the final cloud, I'll call it, of electrons from the last dynode stage is going to strike the anode, and that is going to produce our output current pulse. So, things we need to think about. Photomultiplier tubes are not all exactly alike. They're physically constructed items. They're manufactured. And so there's going to be differences in construction from tube to tube. Some of those differences are the dynodes themselves. You know, how are they aligned with each other? They're all mechanically held. They're all mechanically constructed. So there's going to be variances from photomultiplier tube to photomultiplier tube. The photocathode coating itself can vary from PMT to PMT, and the response across that PMT itself can vary. So left side of PMT to right side of PMT can vary. So there's a lot of variances that can be that can occur in PMTs, and so we need to know that and understand that for our purposes down the line. Now, PMTs come in two basic families. We have a negative high voltage family and a positive high voltage family. In the early systems, most people, I should say, used positive high voltage system. What happens though is that final stage, we got a high voltage potential there, and our final stage, in order to get the signal go from the final dynode to the anode has to be a higher high potential than the final dynode stage. Well, if my anode's at 1,000 volts and I got this little teeny microvolt pulse sitting on it, I have a microvolt pulse sitting on 1,000 volts DC. I probably don't want to plug that right into an op amp or a transistor. I'm going to blow it up. So we have to AC couple. We have to put a coupling capacitor between the output anode and the first device we're going to interact with. Anytime you pass through components, there can be degradation. So a little better system is actually to go with a negative high voltage system. In a negative high voltage system, we start with a very high negative potential and we go towards zero, which is, it's doing the same thing. We're just starting at the other end of the spectrum. What happens there is my anode is actually at ground potential. Now, it's not like I've got it tied to chassis ground, but it is at a 0 volt potential. Since it's at a 0 volt potential, the pulse is riding directly on a 0 volt potential. I can directly couple that straight to my components. A lot of systems are using that nowadays. And one other thing that I'd like you guys to think about is that this amplification factor that we talked about can be in the range of 1 million. So for a mechanical device to do a 1 million gain amplification is a pretty impressive thing. We take these photomultiplier tubes, these PMTs, and we're going to put them into an array. That's part of Dr. Anger's theory, is we put these in an array. And again, we're going to use the summation of all of the energies seen from all of the PMTs as our energy. That is our energy output. We're going to use the weighted averaging of each individual tube to help us determine where position was. So what we have is we have gamma emissions, we have a scintillation crystal, we have our array. We're going to go through some positioning and energy circuitry, add corrections to it, and we're going to have a final image. So our crystal scintillation, it is literally, again, the energy of the gamma ray striking the crystal, creating a burst of light. That is going to be detected by our photomultiplier tubes. And again, the brightness of the energy, the brightness of the light is directly proportional to the energy of the gamma event. This is useful in determining or distinguishing between isotopes. Remember that light emits in all directions, right? So all of the light pulses that are being scintillated in the crystal don't all go to a PMT. Some of them go the other way, towards the aluminum. Some of them go towards the outside of the glass. So we have an issue there. We also need to remember that the crystal is not perfectly transparent. If we looked at it, it has an opaque white look to it. So because of that, because of the inverse square law, we're going to have diminishing light, a diminishing amount of light from the impact point. That is exactly what we need for helping us determine our position. The PMT is going to detect the light from the crystal. Again, theory is everything is going to see it. Reality is not all tubes are going to have an output that's worth recording. It's going to be down in the noise level. The pulse height of the PMT is determined by the KEV and the location of the event in relation to the crystal, or the PMT location on the crystal. I like to summarize it with a statement, and the shortest statement I can give you is, for each event, a gamma event energy and a gamma position is determined by the PMT's pulse height. So the height of the pulse is going to determine our position, and it's going to determine our gamma energy. So we take that concept and let's put it into some pseudo reality here. I got a crystal down there at the bottom. I have a gamma event that impacted the crystal. It creates light. I got that spray of light going out. The gamma event was directly underneath the center PMT. So that center PMT is going to produce the highest pulse output. It's going to see the most electrons. They're going to get amplified the most. It's going to produce the highest current pulse out. The adjoining, the left and the right, the tubes to the left and the right of the center tube are going to create a smaller output. They've seen less light. The rows outside of those are going to see less light, and so forth. If I take those output pulses and I graph it, and then I bisect where that peak of that pulse is, I draw a perpendicular line. I re-identify where my gamma event happened. If I move my gamma event over, now I placed it in between two PMTs. Those two PMTs are going to see the exact same amplitude. The adjoining ones are going to see the same amplitude. Again, draw my curve, bisect it. I see my location. And that works for, it doesn't matter if it's in between tubes, in the center of a tube, or partially through a tube. Position determines how much light is going to be produced, determines how big the pulse is. Comparing pulses, bisecting it is going to give me a position. So we now have position indication by taking all of our gamma energies. We have an energy component, so we have information that we can apply corrections to. There are 4 general corrections that we're going to have to deal with: PMT balance, energy, linearity, uniformity. It is important to note all of the energies, all of the corrections build upon each other, and the accuracy of any preceding correction is directly determined by if the previous correction was accurate. I can't expect to get a later correction to fix something that an earlier correction had messed up. So PMT balance, how are we going to do that? First of all, what we have to do is we have to think about the fact that we need this. What does PMT balance mean? It means we're going to equalize all of our outputs. Terms you might hear in referring to a PMT balance is a PMT tune or PMT update, auto gain. GE uses intercal. You might hear ZMAP. There's terms for different manufacturers, but they're doing the same thing. They're making the outputs of the PMTs the same. And this is a correction factor that's doing that. It's not really a correction factor, it's an adjustment that is doing that. It's compensating for the dissimilar outputs of the PMTs and the crystals. If we fail to achieve a balance in our PMTs, we're going to have artifacts in our image. Just plain and simple. We are going to have artifacts. So how is this done? We take our output of our PMT and we're going to run it through a preamp. The preamps themselves can be integrated right into the PMT itself. Bottom right picture is a Siemens PMT, and you will notice it's got a bunch of pins sticking up. Those pins are for digital control of the amplifier circuit. On this system, it's actually kind of a hybrid. There's actually a pot to do some mechanical adjustments also. If the digital compensation can't do enough, there's some mechanical compensation that can be added or taken away. Usually, nowadays, your PMT balance is done via computer control. We just tell the computer to do it. It goes through the process. We don't have to mess with it. We sit and watch. On some older systems, it might require total manual adjustment. You might have to physically go and adjust every photomultiplier tube to get a similar output. So how do we do this? How do we create this balance? How do we make sure that we got a balance? First thing we're going to do is we're going to flood the bare crystal, and this is in modern current cameras where they're all automatically tuned. We're going to flood the bare crystal with gamma events. In order to flood it with, referencing back to nuclear medicine itself or radiation itself, we need to have, in order to get a linear dispersion of counts, we're going to need our 5 fields of view. Our inverse square law affects us. What's going to happen is that flooding of the crystal is going to be looked at by the computer, and it's going to make iterative adjustments. It's going to basically look at it, say, this needs to be turned up, that needs to be turned down, make that adjustment, look at it again, make another determination, look at it again, make another determination, and so forth, until everybody's the same. And it's pretty simple to do for the computer because your gamma energy is equivalent to the pulse height. So we can simply use an A to D to measure our pulse height and then use that to make our determination on our preamp adjustment. The second correction. Now we have balanced this camera, and by the way, balancing of the cameras, typically done with technetium. So we have our second correction. It's going to be energy correction. So what is energy correction? Well, there are variances in energy response for various reasons. There's 2 main sources of this. One is a nonlinear response because of your PMT growth. The crystals itself are not perfect, and construction. The other one is that we have a physical response issue. So since crystals aren't growing perfectly, we're going to have to fix that. The other issue, or the secondary issue, was that the response based on position. In between tubes, we have what's called a barrel effect. It's causing a nonlinear response. The curves are the response of a PMT across its face and is causing a nonlinear response. We need to fix that. If you were to look at that physically, what you're going to see is the center of a tube is going to have a higher response on a peak than a area in between tubes. So we're going to fix that with an energy correction. It basically acquires a bunch of counts at a 5 field of view. It's going to look at those counts. It's going to say above peak and below peak, how does this respond? And we're going to fix it. Third one is linearity correction. Linearity correction, after our PMT balance and our energy correction are done, we're still not going to have a perfect picture. You're going to see hot areas. We call it pepperoni pizza a lot of times. That's because of linearity correction. This nonlinear response we talked about already is causing that. The areas in between tubes are going to cause a barrel effect. The areas in the center tubes are going to cause a pincushion effect. We often say that it appears that the events are pulled towards the center of the PMT. So how does that look? Areas in between tubes with a barrel get sucked towards the center of the tube. Events in the center of tubes in between tubes have the barrel discussion get pushed away from the center or the area between tubes. The area in the center of the tubes gets pulled towards the tubes. The result is we have a wavy line for a straight line of exposure. Now, I can draw this up all day, but the best thing to do is look at an actual image. So right-hand picture, this is a picture of a bar phantom where linearity is off. It has been turned off. You will see that in the center areas where we have our pizza effect, the lines get squished together. Areas in between PMTs, you're going to see this barreling, the expansion effect. Top right picture, linearity off. Bottom right picture, linearity on. What do you notice? All my pizza went away. My pepperonis went away. And the lines became straight. This is a correction that is extremely important on cameras. This and PMT balance are the two most important corrections on a camera. How's this done? We have a mechanically uniform dispersion of detectable events, whether it's slits or holes. Those detectable events, they are known. Since it's a mechanically designed item, those events are mechanically known to be in a specific location. By looking at where they appear, where the camera detects them at, and where they should be, I can create offsets. Adding those offsets to the original data makes the bad image on the left look like the good image on the right. Straight lines become straight. Pincushion goes away. I don't have my hot pizzas anymore. The two kinds of phantoms you'll find, the linearity phantom with holes and linearity phantom with slits. The slits come in X and Y phantoms because you need to be able to look at both X and Y. They're just used to determine the straightness. And the computer determines the straightness, creates its compensation point, but it not only creates it for the points themselves, but it interpolates every area in between. So not just the areas where there's a dot are perfect, it fixes everything in between by interpolation. Now we come with flood correction. So flood correction, what is it? There are still some non-uniformities that it's not perfect. So what we're going to do is we're going to fix those slight variations. We should not be using it to fix damage of a collimator. We should not be using it to fix any large irregularities. How are we creating it? Flood correction is done the same way as energy correction. We flood it from 5 fields of view away. We're going to analyze that image and make a correction. Now, most flood corrections are probably done intrinsically. There are some cameras that do it extrinsically, or there's some customers that desire it to be done extrinsically. That's with a collimator on. But here's how it works. I acquire data. Bottom left picture is my acquired data. My acquired data, my good data, nominal area is in the blue. Areas that were hot or cold are in the yellow. Well, the computer acquires a bunch of data, looks at it, and goes, oh, look at that, hot and cold areas. It says, what do I need to do to the hot area? What do I need to do to the cold area to make this image good? And it creates a response correction. Applying the correction to the original image will create a uniform picture. This is a kind of a walkthrough of how corrections affect an image. Top left one, after PMT balance, you notice I have pizza. After energy correction, I still have pizza. Not a lot of difference. Because I tuned with technetium and because I'm imaging technetium, my energy response it does very little. Now, I apply my linearity, top right picture. Once I apply linearity, you notice the image gets much better, and then I apply all corrections. Now, I have significantly enhanced these images to magnify the any irregularities in the image, but the general purpose is, or the general concept is, energy, or I mean, PMT balance energy does, there's very little difference, but you add linearity, it's going to make a huge difference, and all corrections is also going to make a huge difference. So if we were to take this concept, and I have a little story I tell about making cakes. I have my PMT balance, I have my energy correction, my linearity correction, and it's a layer cake. Each layer was made by somebody who didn't really care what they were doing. So we have our PMT, our energy correction, linearity correction, and I stack them together. When I stack them together, I have this pretty ugly looking layer cake. So what are you going to do? We're going to put icing over it. That is our flood correction. Now, if I slab enough icing on this thing with flood correction, because all the flood correction is doing is saying, there's a hot area here, there's a cold area there. If I slab enough icing on this, I can make it look pretty. It can look beautiful. It's uniform. It's perfect. And I can set that out in my showroom window. If I have a person who does corrections properly, my PMT balance is good, my energy correction is good, my linearity correction is good. Those are all added together. What do? I put my icing on it, my flood correction, and what do I get? A good picture. Now, if I have these both sitting side by side, store A and store B, you look at it as a customer from the final result, what are you going to see? You're going to think, oh, they're both good. They're both quality. No, the corrections on the original one, the first one, were junk. They were not proper. I just made it look pretty by doing a flood correction. The second image is with corrections that were properly done, and it looks just as good. The thing is, the corrections not being proper and just being covered up by uniformity correction are actually going to cause problems in our images. Don't be this guy. Don't be the guy who just simply does a flood correction to make it good. That is wrong. It is unethical. It is bad. So this has been a really quick blow through on this. Just wondering if anybody has any questions.
Thank you, Mike. That was very interesting. We've got time for a couple of questions. The first one is there an advantage to either square or round PMTs?
I would say that there's probably a little advantage to the tubes that can fit closer together, such as octagon shaped tubes and square tubes, because there's less area in between tubes. When you put three circles together, there is a triangle in between those three circles, and since that triangle is a kind of a dead zone, it exasperates some of the energy problems and some of the other problems we have.
Okay, so how can I tell if a crystal has a defect such as measles?
It really depends on the camera you're dealing with. Some cameras, the way that they operate shows it much better than others. Like, let's take an ADAC Philips camera. If I was to do off peaks on an ADAC Philips, it's actually quite easy. Well, what I will notice is, in an off peak is using just one side of the photo peak and then using the other side of the photo peak to image. What I will see is an artifact that does not flip or does not change. But really, the only way, if you want me to give you a 100% accurate, this crystal is yellowed, the only way to do it is take the head apart, pull the tube, a tube or the tubes in the affected area out, and look at the crystal visually. That is really the only 100% accurate way to determine it.
Okay, and I think we've got time for one more. Can I correct for yellowed crystals?
Yes, no. Energy correction is going to correct for non-linearity or nonlinear responses to yellowing. So yes, no. It's correcting for it, but still there is an inherent issue with the fact that that area has less response than it should, and the fact that it has less response from it that it should. Well, also let's add in the fact that yellowing doesn't just like, it's not like somebody puts a dime on the crystal and it's there and it's that size. It's always going to be that size. If something's yellowing, it's going to grow. Once yellowing starts, it's like a fungus. is growing. It will continue to yellow, bigger and bigger area. So can I correct for it? Yes. But you're going to come back and you're correct for it again. And is the response of the crystal optimal? No. You know, is it still functional? Yes. But if there's something you can do about it, like let's get another crystal, that would be good.